All right, welcome to Chem 313, lecture number 6 for the summer of 2020 quarter. We are going to review what was talked about in the last lecture. So lecture 5 was our first foray into protein function. And the key take home, I think, from that lecture was the fact that a protein's three-dimensional shape is really what determines its function. And the first function that we looked at for proteins is simply binding of other molecules, which we represent by the generic term L. Capital L means ligand, and don't worry too much about where that term comes from. By the way, ligand can be almost anything you want. It could be another protein molecule for all we know. But the language is kept general so that we can apply the same sort of analysis to any kind of protein and any kind of other molecule that we can think of. So we said that binding can be represented, assuming that you have only one spot on your protein that will bind, by a sort of reaction that looks like this. PL is a complex. So if we make a couple of assumptions, let's assume for one thing that our concentration of ligand is much greater than our concentration of protein, which is more often than not going to be the case. And then let's assume that we are at equilibrium. All right, so I mentioned this assumption in the last lecture, but I don't think I quite spelled it out clearly enough, so I'm going to spell it out very clearly this time. If binding is at an equilibrium, what that means is that the rate of binding must equal the rate of unbinding. Right? Because at equilibrium, the forward reaction and the reverse reaction are balanced. So what is our rate of binding? Well, our rate of binding we could express as a rate constant, which we will call K on, times our populations or concentrations of free protein and free ligand. And our rate of unbinding is going to be a different rate constant, K off, times the concentration of complex. And if we make this assumption, we can come up with this equilibrium constant Kd, which we call a dissociation constant. And what is that? That's the equilibrium constant for dissociation of the complex. So in other words, for the reverse of the equilibrium shown above. So our Kd is equal to products over reactants at equilibrium. It's also going to be equal to K off divided by K on. Now we care about KDs an awful lot because a KD measures the strength of binding. If you have a lower KD, that implies stronger binding. And vice versa, a higher KD means you have weaker binding. And we said before that we can define this quantity called theta. Theta is what's called the fractional saturation. Theta is also sometimes represented by a capital Y, And I think you're going to see a capital Y in some practice problems in our homeworks and in our worksheets later on. Anyway, what is theta? It's the concentration of bound binding sites. So in other words, binding sites on your protein that have L bound to them, divided by total binding sites. Or if you have one binding site per protein, then theta is going to be equal to PL over PL plus P. And we've said before that if you make these assumptions that we already talked about, it can be shown that theta is going to be equal to concentration of ligand over concentration of ligand plus Kd. And if you were to make a graph of theta as a function of ligand concentration, you would get a curve that trends towards theta equal to 1 without ever quite getting there. And if you were to go down on the y-axis to the spot where theta is equal to 1/2 and trace that over to the line and then down to the x-axis, at this point, your ligand concentration is equal to Kd. So a more operational definition of Kd is that Kd is the concentration of ligand that gives 1/2 of protein molecules bound to ligand. In other words, half saturation. We also talked about this class of proteins that exhibit what's called cooperative binding. And cooperative binding is what exists when you have at least the following situations. You have multiple binding sites on each protein. And you also have multiple conformations of your protein. With different KDs. And the usual case is that we would have a low KD structure that is dominant when we have a low concentration of our ligand, a high KD structure, and a low KD structure that is dominant at a high concentration of ligand. There are exceptions, but that's the usual case. And in the situation when this occurs, your theta curve becomes S-shaped. It still levels off at 1, but what we're actually seeing here is a superposition What we're seeing here is a superposition of two hyperbolic curves. The protein starts off in one non-cooperative binding structure that has a high Kd. We call that structure T. And then our protein flips over to a different structure that has a lower Kd. We call that one R. And cooperative binding is very important. We're going to see it again in the end of today's lecture. So today's lecture is going to be related to binding. It's a subject that depends on binding, but it's something that we have to spend a few lectures talking about. And that is enzymes. All right, so let's define what an enzyme is. So enzymes are going to be our probably most in-depth investigation of protein structure. Enzymes are proteins that act as catalysts for a chemical reaction. To refresh your memory, a catalyst is any substance that speeds up a chemical reaction without being consumed by the reaction. It's present, and its presence accelerates the chemical reaction, but it's not itself a reactant. So we're going to see several examples of this in our textbook. Almost all chemical reactions in biology are catalyzed by enzymes. So just to give you a couple of examples of different enzymes, here's one that we're going to use as an example later in today's lecture, and you saw it earlier in the last lecture, in lecture 5, and that's glucokinase. So glucokinase is the enzyme that catalyzes this reaction. Glucose plus ATP reacts to give glucose 6-phosphate and ADP. This diagram is showing what the enzyme looks like by itself, and this is the enzyme bound to glucose, which is in red. Another example of an enzyme would be chymotrypsin. So chymotrypsin is an example of a protease, which is an enzyme that catalyzes the cutting of another protein. And so chymotrypsin's reaction would be another protein, that would be its reactant, plus water gives you 2 protein chains. So if you're interested in these enzymes, the book talks about both of them. I'm going to refer you to the textbook if you're interested, but in this course, you're only responsible for what is in the lecture. And I'm going to use these simply as examples. We're not going to talk about their mechanisms in this course. One thing you should notice from this slide, though, is that most enzymes act as catalysts for only one, or in some cases, a few closely related reactions. So there are no general purpose enzymes. Most enzymes have evolved to catalyze one specific reaction, and they're completely ineffective in every other reaction. And that's very important. If there was a general purpose enzyme, biology would be chaos. So this slide is related to that last point. We can classify enzymes according to the types of reactions that they catalyze. So there's this scheme called the EC scheme, or enzyme classification. It's sort of a hierarchical scheme for classifying an enzyme according to the reaction that it catalyzes. And so what happens is that all of our enzymes are broken down into one of 6 classes: oxidoreductases, transferases, hydrolases, lyases, isomerases, and ligases. So these are broad classes of chemical reactions: transfer of electrons, transfer of groups within molecules. And then underneath that, we have several different subclasses of enzymes. So for example, lyases, which are adding water to double bonds, right? So a lyase adds a group to a double bond. So our subclass would be adding water to double bonds. And then a subclass would be in fatty acids. And then we could have probably a subclass, which would be in a particular fatty acid. Okay? There's officially recognized actually 7 enzyme classes. This table is, 12 years old. Since then, they've come up with a 7th class, and that is translocases, also known as channels. And that was not recognized as an enzyme until just a couple of years ago, but they have many enzyme-related properties, so I think it's worth mentioning it now. And these catalyze movement of a solute across a lipid bilayer. So that doesn't sound like a chemical reaction, and technically I guess it's not a chemical reaction, but it behaves in many respects like a chemical reaction, and these proteins, the translocases or channels, have enzyme-like behavior, so we classify those as enzymes. You'll see those later in this course. Anyway, most enzymes usually catalyze only one reaction, which we've already said before. That's why this enzyme classification scheme makes sense. So that means that enzymes are said to be selective. They catalyze only one type of reaction. And they are active on only one or a few substrates. So a substrate is just the term we use for the reactant of a chemical reaction. So for example, glucokinase is both specific and selective. It transfers phosphate from ATP to glucose. Well, it only uses ATP and glucose as its substrates. It does not use other substrates, so therefore it's a specific enzyme. And it forms only one particular product, which is glucose 6-phosphate, not glucose 1-phosphate or glucose 2-phosphate. So it's also selective. And this is true of most enzymes. So our question now becomes, how do enzymes increase the rate of a reaction? Let's take it very, very simple and assume that we have a unimolecular reaction. A forms B, right? Let's say, for the sake of argument, to make things as simple as possible, we have no B at our initial condition. So that means that we don't have to worry about any reverse reaction. And let's further assume that this reaction is elementary, which means that it happens exactly literally as it's written. A molecule of A changes to a molecule of B. There's no intermediate where it changes into a molecule of C first and then that turns into B. It happens exactly as it's written. So to refresh your memory of chemical kinetics, the rate of this reaction is going to be defined as the change in the concentration of B with time. And if our reaction is elementary, that should be equivalent to the negative of the change in the concentration of A with time, right? So you can think of as rate of a reaction is a slope of a concentration versus time graph. We're going to see that in a moment on the next slide. All right, so if our rate is equal to dB dt and our reaction is elementary and we have 0 concentration of B, so we don't have to worry about the reverse reaction, our rate in the forward direction is going to be equal to K, which is a rate constant, times our concentration of A initially. So what's this rate constant? Our rate constant, K, can be further described as a constant times E to the negative E act over RT. R is your gas constant, T is your temperature in Kelvin. So what is this E act? E act is the difference in free energy between the reactants and the transition state. What's the transition state? So the transition state is equal to the highest energy point in our reaction. So the transition state is the point where A is right balanced on a pinhead in the middle of the transition from A to B. And the transition state is always, by definition, the point of highest energy in the process of going from A to B. So that's what this diagram is supposed to show you. It's a reaction coordinate diagram. Reaction coordinate is essentially how much your reaction mixture is similar to product. And the transition state is the highest energy point in this process. Our transition state is symbolized by the double dagger symbol. So our activation energy is going to be equal to this energy difference, the difference between our reactants, which is what we started with, and our transition state. So a higher activation energy means you're going to have a smaller rate constant K, and therefore you're going to get a slower reaction. So how do enzymes actually increase the rate of a reaction? Well, the way enzymes increase the rate of the reaction is they simply lower that activation energy. Right? So if this is the same reaction in the presence of an enzyme, we see that our activation energy is lower, and therefore our rate constant K is going to be higher, and that gives us a faster reaction. Right? We could summarize that by saying reactions go faster when the activation energy is lower, so enzymes just lower the activation energy of a reaction. Now, how do they do this? We're going to talk about that later. We will discuss how it is that enzymes actually lower the free energy of a reaction, but we're not going to talk about that in today's lecture. One thing that I do want to point out, however, is that if you compare these two curves, notice something. The difference in free energy between reactants and products does not change. So enzyme catalysis in general, does not change the free energy of the reaction. It changes the free energy of the transition state, but that's something different. So because the enzyme catalysis does not change the free energy of the reaction, it does not change the amount of product present at equilibrium. Catalysis simply means that you get to equilibrium faster, but it does not change what the equilibrium itself looks like. All right, we're going to take an in-depth look at how enzymes actually behave. And we're going to use our glucokinase reaction as our sort of test case. So it turns out that enzymes, compared to other catalysts, have some sort of quirks. They do things that are somewhat different than we would expect. So we're going to carry out an experiment using glucokinase. We're going to have a reaction mixture containing a varying amount of glucose and a constant concentration of ATP. And our concentration of ATP and glucose are going to be much greater than our concentration of enzyme. So in other words, all we're going to do here is take a test tube. We're going to throw in glucose and ATP and glucokinase. And then we're going to measure our concentration of glucose 6-phosphate as a function of time. After mixing. So let's do that reaction. Notice that we're starting off with no products. We're starting off with just reactants and our enzyme. So what would we observe? So what we would observe would be something that looked like this. We've got our concentration of glucose 6-phosphate, which we could possibly measure with a spectrophotometer or something like that. Time on the x-axis. And what we would observe is that our glucose 6-phosphate concentration, it's going to start off at 0 and increase approximately linearly. Now, eventually the reaction is going to approach equilibrium, and when that happens, it would flatten out. But we're not going to show that part. We're going to worry just about the beginning of this reaction. All right, now we said before that we're going to do this experiment with a varying concentration of glucose. So this is what would happen at a low concentration of glucose, low initial concentration of glucose. If we were to raise glucose concentration, what we would see is that the reaction speeds up, right? We get our glucose 6-phosphate faster. And if we kept doing this, it would keep increasing. But here's the thing. Every time you increased your glucose concentration, you get diminishing returns until eventually you got to a point where adding more glucose didn't increase the rate of this reaction at all. So we said before that a rate of a reaction can be expressed as a slope. So let's call the slope of these curves V0. So V for velocity, and 0 meaning that we're going to measure the slope right at the point where time is equal to 0, because at that point in time we know we have no products, so we don't have to worry about the reverse reaction taking place. If you were to do this experiment and graph V0 as a function of glucose concentration, initial glucose concentration that is, you would get points on a curve that sort of look like this. They're increasing but leveling off. And if you were to carry this up to the point where the reaction rate doesn't increase at all, you would get velocity equal to this value we call Vmax. All right, so Vmax is the maximal reaction rate at this concentration of enzyme. And you would notice, if you were to do this at different concentration of enzyme, I'm not going to show you what the graph looks like, but I'll mention this in words. If your concentration of enzyme were to increase, then Vmax would also increase. But the shape of the curve would not change. It would look like this. So essentially what we have here is a hyperbolic curve. And that means it levels off at high concentrations of glucose. And the question is why? So this is not something that you would see in other catalysts. So for example, in organic chemistry, you probably saw that, addition of a small amount of acid can increase the rate of an ester hydrolysis reaction or something like that. So that is true regardless of the concentration of your reactants. If you increase the concentration of your reactants, the rate of the reaction just keeps on going. It doesn't level off like this. Why do we see this leveling off behavior, which is almost unique to enzymes? So to answer that question, we need some sort of a model, right? A simplified model for how enzyme catalysis works. Let's assume the simplest possible case of a reaction. We have a substrate reacting to form a product. So this is the situation like we saw on the earlier slide where we just had A forming B, unimolecular reaction. And this reaction takes place with catalysis by an enzyme. And we're assuming that the rate of the reaction without enzyme is so slow that we don't even observe it. Okay, so what we're going to do is this. We're going to make some assumptions and see what this assumption leads us to. Do we see behavior that matches our experiment? We're going to assume that we have a reversible binding to our substrate. So in other words, our substrate and our enzyme give us an enzyme substrate complex. We can have K-ons and we can have K-offs. So this is looking just like what we saw at the beginning of the talk with binding of a ligand to a protein, right? Reversible binding to form a complex. Okay, but we have to add an additional step here. Our additional step is that once our substrate is bound, it can either unbind or react. So we've already included the possibility of it unbinding. That would be going back to enzyme plus substrate. But we need a reaction. And there's our reaction. So once you have your substrate complex, you can either fall apart, your substrate just falls out, or it changes to a product. And then we say that our product is going to be immediately released. So what this means is that we have no enzyme product complex. This is kind of not the greatest assumption, but it makes the math easier, which is why we're doing this. And then lastly, the most important assumption of this whole model here, which makes this doable, is that we are assuming steady state. So what does that mean? That means that the rate of binding is equal to the rate of unbinding plus the rate of the reaction. Or in other words, the concentration of enzyme substrate complex is constant over time. And then we have a couple of miscellaneous assumptions we need to make here. We're going to assume that our reaction is either irreversible or our product concentration is so low that we don't have to consider the reverse reaction, right? That's why I drew the final step as a one-directional arrow instead of a reverse direction. And then we also have to further make the assumption that our substrate concentration is greater than our enzyme concentration. In biology, this is usually the case. Enzymes are usually present at very low concentrations. So if you really care about why each of these assumptions is necessary, I'm going to refer you to the textbook. But the result of this entire model is this equation right here. We call this the Michaelis-Menten equation. The Michaelis-Menten equation expresses our reaction rate, V0, as a function of our initial substrate concentration. If you care about the derivation of this equation, I'm not going to go over it in class, but you can have a look at the textbook. It goes through, I think, a reasonable explanation. So what do we see in this equation? We see that our V0 is equal to Vmax, remember that's the value that we level off at, times substrate concentration divided by Km plus substrate concentration. What's this Km? Km is called the Michaelis constant. All right, Km is a property of an enzyme substrate pair. Right? Each substrate on a given enzyme is going to have its own Km. So what is Km? So you should notice that this equation looks an awful lot like our expression last time for fractional saturation. We had ligand concentration divided by Kd plus ligand concentration. What Km does is Km measures the, I want to say, effectiveness of enzyme substrate binding. What do I mean by effectiveness? I mean essentially the likelihood of reaction once the substrate is bound to the enzyme. Okay? It is not the same thing as the strength of binding. Right? It's oftentimes confused with the strength of binding, but Km does not reflect the strength of binding. Strength of binding is reflected by Kd, right? And yes, there is a Kd for an enzyme binding to its substrate, but what we're caring about here is the reaction rates, right? So it's kind of like a Kd for a reaction. That's what the Km is. But it is very much like a Kd. A lower Km implies more effective binding. And it's like Kd in another respect. Km is equal to the substrate concentration at which your initial velocity is equal to Vmax over 2. So that means that if we were to measure our Vmax for our chemical reaction, follow it down to the point where V0 is equal to 1/2 of Vmax, and then trace that over to our x-axis, at this point, our substrate concentration would be equal to our Km. And so just like we saw with KDs, you can think of a low Km as being reflective of it only takes a little bit of substrate to get you halfway to Vmax, right? So if your Km is very low, what does that mean? That means that only a little substrate is necessary to get the reaction going fast. And the whole key to the Michaelis-Menten model is the fact that binding is saturable. That's what's the key to this whole observation that we get this leveling off of our rate. When we are way out here, approaching Vmax, that means that most of our enzymes have substrate bound. So saturation of binding is what leads to the leveling off of our rate. So that's what Km is all about. What about Vmax? So if we go back to our reaction that we saw on the last page, we said before that we can define a K-on rate constant for binding of the substrate to the enzyme and a K-off for unbinding. But then there's a second step here where we have reaction. That reaction has a rate constant associated with it called Kcat, right? So the rate of the reaction that we observe is going to be equal to Kcat times the concentration of our complex. So where does this term Kcat come from? What's the cat? Well, the cat means that this is our rate constant for catalysis. This is related to the lowering of our activation energy. All right, a lower activation energy means you'll have a higher Kcat, which means that you'll have a faster reaction. So it can be shown that the maximum rate of our reaction, Vmax, is equal to Kcat times the total concentration of our enzyme. Why is that? Well, let's imagine that if we have a huge concentration of substrate, let's say that our substrate concentration is very much greater than Km. Well, at that point, all enzyme will be bound. So our concentration of enzyme substrate complex must equal the total concentration of our enzyme, right? And at that point, our velocity is going to be equal to Vmax. So Vmax is equal to Kcat times the concentration of enzyme. This accounts for the fact that Vmax increases as enzyme concentration increases. So the two parameters in the Michaelis-Menten equation reflect different aspects of our enzyme-catalyzed reaction. Km tells us about binding. A lower Km means you have more effective binding. That means binding that's more likely to result in a reaction. Vmax has to do with the reaction itself. Right? Higher Vmax implies a greater reduction of activation energy. And generally speaking, these two parameters are independent of one another. So you can have an enzyme that has a very high Vmax, but it's also got a very high Km. Or you can have very low on both, right? These are independent of one another. You can, by altering the structure of the enzyme, change Vmax without having any effect at all on Km. That is possible. And we're going to see examples of how that might happen over the next couple of lectures and over the next couple of worksheets. So these two parameters are independent and they deal with different stages of our enzyme catalyzed reaction. The Km deals with the binding step and the Vmax deals with the reaction step. So an important point that I want to make is that our Vmax and our Km must be measured empirically. It's not something that you can easily guess from first principles. So you have to actually do an experiment like this where you measure the rate of your reaction at different concentrations of substrate and then figure out your Km and your Vmax just from the shape of the graph. So typically this is going to be done with some sort of a nonlinear curve fit. In the old days, before computers were widespread, nonlinear curve fits were a huge pain, and people would go to extreme lengths to convert any equation they could into a linear form so they could do a linear regression just on graph paper, which is possible by hand. Trying to do a nonlinear regression by hand is extremely hard. So if we take our Michaelis-Menten equation and do 1 over both sides, that gives us a linear function. So if we do that, we end up with this modified version of the Michaelis-Menten equation. This is what's called the Lineweaver-Burke equation. And it is a linear equation. 1 over our velocity is our y. 1 over substrate concentration is our variable x. Km over Vmax is your slope, and 1 over Vmax is your intercept. So a Lineweaver-Burke graph, as opposed to a Michaelis-Menten graph, gives you a straight line. The y-intercept is 1 over Vmax, and the slope of the line is equal to Km over Vmax. And so as long as you have the equation to the line, you can figure out exactly what your Km and Vmax are. A lot of textbooks also point out the fact, this is much less useful, but I'll include it for completeness. Our x-intercept is equal to negative 1 over Km. So Lineweaver-Burke equations are not as widely used as they once were, because now we've got easy access to computers and doing a nonlinear curve fit is pretty easy. But Lineweaver-Burke equations are useful for dealing with enzyme inhibitors, which we're going to talk about in a later lecture, which is why we still teach these. So I'm planting that seed in your mind for you guys to look at later on. So as far as interpreting these equations and graphs go, I'm going to have you guys check out homework 3, which has some practice problems of about the level of depth that I expect you to understand these models. Now, we said before that Michaelis-Menten behavior comes from having saturable binding. And we talked about in the last lecture how some protein-ligand binding reactions are cooperative, where you have more than one KD. And you may be wondering, well, what happens if you have an enzyme that binds its substrate cooperatively? And that does happen. That's what we have, we call cooperative enzymes. And it's very similar to cooperative binding, just with a reaction. So typically what happens is we start off in some sort of a T state, which means that we've got ineffective binding of our substrate and our enzyme. So once again, this only applies if you've got multiple binding sites, so multiple reaction sites on your enzyme, and that you can change to a different structure that binds differently. So we're going to start off in a state that has a fairly high Km for our substrate, but as more substrate binds, we switch to a structure that has more effective binding and a lower Km. And that would be our R state. And as you've probably guessed, what does that do to our Michaelis-Menten curve? Well, it changes it to an S-shaped curve, because we now have a superposition of two different structures. In effect, it's almost as if we have two different enzymes. We have a weak binding structure that we start off in, and then we switch over to a strong binding structure. Now, essentially what happens in a cooperative enzyme is that we switch from a high Km to a low Km structure. The Vmax does not change. That's the usual case. There are some rare enzymes where you have two structures and it's not the Km that changes, it's the Vmax that changes. But we're not going to talk about those. It's not common enough to be worth dealing with. But once again, what we have is two separate curves, two separate regular Michaelis-Menten curves. We start off in the structure that has a high Km, so not very effective binding. But once we have a few substrates bound, we get a change in conformation. And this change in conformation makes it so that binding becomes easier, and then we switch over to this low Km structure. And that gives us this S-shaped or sigmoidal curve. And once again, just like we saw last time with binding, this means that we can get a big change in our initial rate from a relatively small change in our substrate concentration, which is handy in a lot of biological situations. All right. There's another situation that oftentimes comes up in cooperative binding enzymes, and that's what's called allostery. So allostery is a general term. That means whenever you bind some substance other than the substrate, that affects substrate binding. So I'm going to give you guys an example here. Let's say that we have some allosteric regulator, which I'm going to draw as a little triangle. And so this triangle is going to bind on some other part of our enzyme molecule, not the part where the substrate binds, but some other part of the molecule. And when it binds, it changes the enzyme from the T structure to the R structure. So we switch from our our high Km structure to our low Km structure without ever binding any substrate. So once our regulator has bound, what does that mean? Well, that means now it's going to be very easy for our substrate to bind, and we get an activation. Okay, so an allosteric activator makes it easier for enzymes to switch from our T structure to our R structure. And you can imagine a different scenario where a different regulator, probably should have drawn that differently, also binds to some other site, but in this case, it locks the enzyme in the T structure. So that essentially no matter how many substrate molecules bind, we're always in T. So this is a case of an allosteric inhibitor. It makes it harder for the enzyme to switch. From the T structure to the R structure. So you may wonder, are there allosteric activators or inhibitors for non-cooperative enzymes? And the answer is yes, but they're not very common. This is something that you typically only see with cooperative enzymes. So what do allosteric activators and inhibitors do to our reaction rates? Well, remember, if we have a cooperative enzyme, then we necessarily are going to have a velocity versus substrate concentration curve that's going to be S-shaped, so it'll look something like this. And we said before that if we have an inhibitor, the inhibitor is going to make it harder for the enzyme to switch from T to R. So I'm going to draw that case as green. If we have an allosteric inhibitor, allosteric inhibitors favor the T structure. What does that mean? Well, that means that when the allosteric inhibitor is bound to our enzyme, the enzyme is less likely, or it takes more substrate, is another way of putting it, to switch from T to R. Well, you'll recall that on our velocity curve, the T structure is what dominates at low concentration of substrates. So that means that in the presence of an allosteric inhibitor, we're going to stay in that T structure for longer. So an inhibitor is going to shift the V0 curve to the right. Why? Because that follows the Michaelis-Menten curve for the T state. In extreme cases, if you have an inhibitor that truly locks the enzyme in the T structure, then what you would end up with is a Michaelis-Menten curve that corresponds to the T state. Now let's look at what happens in the presence of an allosteric activator. So we said that an allosteric activator favors the R state. Which means our enzyme is more likely to switch from T to R. And you'll recall that if this is the velocity curve for the R structure, then that means that it's going to become easier for our enzyme to shift over into that structure. And our curve will shift left. And in extreme cases, if you had an allosteric activator that locked the enzyme in the R structure, what you would see is a Michaelis-Menten-like curve that that matches that of the R state. So an important point to note about allosteric regulators. Allosteric regulators generally speaking, they change the number of substrates that must bind to result in the T to R shift. Generally speaking, they do not change the Kms or the Vmax of T or R states. There are rare examples of allosteric regulators that do that, but generally speaking, they don't. All allosteric regulators do is they make it easier or harder to switch from the T structure to the R structure, but they don't change the T structures or the R structures themselves. So for examples, once again, there are plenty of example problems on homework 3 and on worksheets 4 and 5, which will be up on Canvas this week. And so I encourage you to do all the practice problems you can, because understanding qualitatively what's happening when you have a Michaelis-Menten enzyme versus an allosteric enzyme and why these curves are shaped the way they are, that's very important for doing well in this course. I'll see you guys next time.